All right. Well, welcome to your first online lecture. Um, so we're looking at section 4.7, which is uh, entitled Applied Optimization Problems. Let me simplify that a little bit. Basically, what we're looking at is story problems where we are trying to find minimums and maximums. We are trying to optimize them. All right. And so we'll work through a few examples here to give you an idea, but in the end, they are all problems like we did before when we were finding minimums and maximums. And so um, that's what we're working on. So if you can remember how you found the minimums and maximums before of just a function, right? You needed the derivative, and then you needed to find the critical points of that derivative, and then you needed to see if there were minimums or maximums. And that's what we're going to do here. Um, but instead of working from just a generic function, we're going to work from a function that is generated by kind of a story problem, an application problem. All right. And so let's look right here at this example, maximizing the area of a garden. So a rectangular garden is to be constructed using a rock wall as one side of the garden. All right. So let's make the rock wall this right there. The rock wall is one side of the garden, and then wire fencing on the other three sides. So one, two, three, and there's our rectangular garden. Given 100 foot of fencing of wire fencing, determine the dimensions that would create the garden of maximum area. And then what is the maximum area? Now, the first thing to remember to realize is, given these circumstances, you could create a variety of different sized gardens. So there's a rock wall. I've got to use 100 meters of fencing, so I could create a garden like this, where it's 1 foot by 1 foot by 98, right? And that is a real skinny garden, but it fits the requirements. Notice the area of that one is base times height, 1 times 98. So it's just 98. Or I could do something like this, right? I could say, oh, well, let's make the sides here, I don't know, 20 and 20. And then that makes this, 60? There's 100 feet of fencing. Now all of a sudden that has an area of 1,200. Or I could do it like this. I could make kind of a tall. This is not to scale, of course. So maybe I make it like this, where I'm like 45, 45, and 10. Right? That's using all my fencing. But that particular garden has a area of 450. So again, the area here is 450. The area here is 1,200. The area here is 98. And so, obviously, depending on how we um, build our fence, we're going to get the gardens of different area, all using 100 foot of fence. And so the question is, how can we do this so we get the most area? Obviously, 98 is not very much area. 1,200 seems like a lot, but is that the most? So what we're going to do is we're going to approach it like this. We're going to say, okay, we don't know the dimensions of our garden, so we call this one X. We call this one X, right? Because it's a rectangle, and we'll call this one Y. And those are our three unknowns. And one of the things that you'll learn as you go through this process, and we've already seen, is we really don't want to have uh, more than one variable. We don't want x's and y's. We just want x's, for instance. So we can actually say not use y there, but we could use 100 minus 2x, because that side right there, that top side, is the rest of the 100 feet of fencing after we take away the two x's to make the sides. So if we replace the y with 100 minus 2x, then all of a sudden we're dealing with x's only. And so, of course, the formula for the area of a rectangle like that is just base, I guess that's the height, but base times height, or 100x minus 2x squared. So depending on what we choose as the side of our rectangle, it could be 45, it could be 20, it could be 1. Depending on what we choose as the side of our rectangle, we can plug that in for x, and that will give us our um, our area. All right. But the question is, we want to find the maximum area, the dimensions that give us the maximum area. So of course that's going to be that right there is saying find the maximum of this function. So it's saying, all right, well, you're going to need the derivative, which is 100 minus 4x. And of course, we set that equal to 0, right, to find the critical points. And that gives us, with just a little work, x equals 25. So if we create a rectangle with the sides of 25 and 25, that means the top is 50, then that's going to give us the maximum area. So the answer to the first question is, what dimensions give us the maximum area? And I guess you write that as 25 by 50, right? And then the second question is, what is the maximum area? And that's where you actually take your value that maximizes and you plug it in to a of x. So let's do it this way. Right, let's go here. A of 25 is 100 times 25 minus 2 times 25 squared. Right, just plugging that in. So 2500 minus 625 minus what's that? 1350 or 1250, excuse me, equals 1250 in square feet. And so that's the maximum area we could get. And we get that by creating a garden that is 25 by 50. And notice, we weren't too far off right here. We got up to 1200 just guessing and messing around. But in reality, what we need is the dimensions of 25 by 50. So there we go. That's a maximization problem. You see it in the end, it's just finding the maximums of a function. The tricky part is the first part where you build the function from the story problem.